All right, I think we're ready to start. Welcome to our first webinar. I'm welcome to the Faculty of Engineering and IT here at the University of Melbourne. My name is Guillermo Narciso, and before we start, we'd like to acknowledge the traditional owners on the land in which we work and we meet today, the Wurundjeri people from the Kulin Nations. We have people joining online, as well as people here. Doing these hybrid events is always a challenge, but hopefully it will work out. We are recording the session. If anyone has an issue with that, please let me know and we'll deal with it later. But I would like to welcome you all today, and our speaker and host of the event, Steve Crowley and Steve Jarvis. Steve, so easy to remember.
The Steve.
So the floor is yours, Steve.
Yeah. Hi, everybody. Thanks, everybody, for coming to our inaugural seminar, which is exciting. I think Guillermo's just welcomed you all, so welcome online and in person. It's nice to see some familiar faces and some new faces. I'm Steve Crowley. I'm the chair of the Australasian Renewable Earth Energy Association, known as AREEA, and I'm also a director of Scott Consulting. Just to run through, so we've done the welcome. I'm just going to spend probably 5 minutes just running through who AREEA are and what we're trying to achieve. And then following that, Steve Jarvis is going to present a case study from New Zealand. And then we'll field some questions at the end. And then we've got refreshments outside for those that can stay and join us. So who are AREEA? So AREEA, we're an industry body, and we've been set up to support and develop the ground source heat pump industry in Australia and New Zealand. Those of you in the industry may have heard of ICSPA and the Ground Source Heat Pump Association in the UK. So we're a very similar body to them. We have been in operation approximately 2 years now. We incorporated as a company limited by guarantees, or a not-for-profit organisation. And we're also, in the last 2 years, we've registered as a charity with the Australian Charities and Not-for-Profit Commission, with very defined goals as to what we need to do to maintain that charitable status. We have, in the last 2 years, set up our processes and set up our organisational structure. We have currently a board of about 9 people. And that ranges across academics, industry, professionals, consultants, installers and other designers. And we've been working hard to try and push this thing along and get it to a place where we're happy to sort of take it out to the wider world, which is about now. We've set up memorandums of understanding with both the International Ground Source Heat Pump Association in the US and the Ground Source Heat Pump Association in the UK. Where we're working closely with them, accreditations and affiliations with them, and we utilise their technical literature and vice versa once we develop our own, and standards, and potentially training as well. So membership of the association can be either individual or as a company, and membership is voluntary. You know, anybody can join. It's voluntary. If you want to actually put any time in to help, it's not there's no paid representatives of AREEA. So what's our primary goal? So our primary goal is to advance the natural environment by application of energy efficient renewable energy technologies. I mean, specifically, it's the use of ground source heat pumps, but if there are other technologies that would be involved, we would also welcome them in eventually into the association. Our objectives, and these are some of our objectives as a company limited by guarantee, but it's also, sorry, just get rid of that. these are also our charitable objectives as well. So training and certification, that's where we're trying to head next, is to start training people in design and install. At the moment, there is no recognised training of ground source in Australia or New Zealand. And so we're trying to get it to a stage where people will have some comfort that the designers and the installers working in the industry have been trained to a certain level, and we can guarantee the quality of both design and install. We're going to try and set up industry standards and specifications. So we started working through that. At the moment, most people working and designing in Australia and installing work to either IGSPA or Ground Source Heat Pump of Australia standards. Eventually, we want to set up our own, and we started working towards that, so that we're actually looking at specific Australian and New Zealand conditions. We want to be a resource for technical information. We want to educate the market in renewable earth technology. Research and development, you know, with the academics that we have involved, we're looking at how we can develop and research new ways of installing these technologies. We want to partner with other sustainable industry providers such as the AGA, and we want to have federal, state and local government advocacy. So they're our primary objectives. And so that's in a nutshell who we are. I don't want to bang on too long because we're really here to hear a case study, but if anybody's got any further questions about who we are and what we're doing, or if you want to become a member, then come and talk to us afterwards. I'll now pass over to Steve, who's going to talk about the headwaters, Glen Orkney. Thank you.
So first thing I've got to do is work out how to get it onto the other PowerPoint presentation. Good at doing ground source heat pumps, no idea how to use a computer. If anybody wants to do a scan of the AREEA, we've also have that on the last slide that we'll leave up in our presentation, so you can always grab a QR code off of that. Just while Glenn sets that up for us, how many people are already working with ground source heat pumps? Is there anybody that's already sort of working in the industry or designing, or how many people know about ground source heat pumps? That sort of have a bit of an understanding about what they are, what they do. Okay, a fair few of us. How many here just for finger food? Okay, yeah, so my name's Steve Jarvis, coming over obviously from the UK originally, living in New Zealand now. It's quite ironic to have two Steves from England in the same room talking about ground source heat pumps. Bit of a change. I sort of started off in the heating industry in the UK, mainly with gas boilers. Moved to New Zealand mid-90s to find out that pretty much everyone had a wood fire and a jumper. So it was quite good to sort of see the development of heat pumps, and then it moving on to the development of ground source heat pumps. And we were sort of lucky enough to have been in the right place at the right time to have quite a lot to do with that development in New Zealand. So about 4 years ago, we did a project in Glenorchy, which is right down the bottom end of New Zealand, at the bottom of the South Island, next stop Antarctica, so relatively cold. It's an eco-retreat. So a lot of time and effort and money was put into showcasing renewable energies and basically good building standards, etc., to work to. So it wasn't just about, sort of ground source or anything. So what I'll do is start flicking through some of these slides. There we go. So told you I wasn't good at driving. Right, so this was New Zealand's first net zero energy visitor accommodation project, put together by Paul and Debbie Brainard, two American philanthropists that had a holiday home in Glenorchy, and they saw that the campground was pretty run down. The existing one was there, and they decided that they would like to use the campground to sort of showcase energy efficiency, etc. So they had a vision, which was, just to generate a thriving business that's environmentally and financially sustainable. But all of the profit from the eco retreat goes back to the local community. larger world. So yeah, we're really grateful for the work that they've done for Glenorchy. So their goals, quite a few different goals. We were obviously tied in on the hydraulic side. So main thing for us was 50% less energy to be used. And this is based on a standard similar sort of campground scenario. So use 50% less water and 50% less energy. 60 beds, 25 sort of living spaces. So reasonable size project. And it was built under what was called the Living Building Challenge. Living Building Challenge is mainly an American environmental building. Imagine it's sort of like Green Star on steroids. So, but the difference between this and Green Star is the Living Building Challenge brings in things like equity and beauty, health and happiness. So it's not literally just driven about cost savings and environmental savings. So it's about encompassing everything. It's a really cool, and you can look up LBC and there's some amazing stuff they've done. So there was only one other LBC project that's been done in New Zealand before, which was a residential. So this was the first time anybody had tried to do an LBC commercial project. There's a lot of work. So how did Ground Source help them meet their goals? So the main goals of us to sort of help them be a part of that Living Building Challenge was to work on energy efficiency and the low impact of mechanical equipment on a project. Obviously, being an eco retreat, noise would have been a big issue for us, which was one of the drivers of moving away from air source heat pumps, because we didn't want the noise from outside, and the visual impact of mechanical plant as well. So the beauty of ground source heat pumps is they're an internal unit and they're in an insulated soundproof box. So they're very quiet and you can plonk them in a plant room, out of sight, out of way, which also makes it a lot easier for maintenance as well. Maintenance crews just go to one spot to deal with all mechanical plant. Just a few photos of the project. So this was a test rig that we set up. Bit of shiny pipe work there for the engineers. So on the efficient energy side, so this was some of our sort of driving factors. For a typical campground, heating and hot water use would be 75% of the energy requirement for a building. So obviously for them to meet a net zero goal, that was the big ticket item for us to work on. And then obviously to assist with that even further was using ground source heat pumps just to get those coefficiency of performances up from an air source heat pump. So we're in a very cold climate down there. This morning was 3 degrees, so it's quite a bit colder than here. So we're a heating only system with no cooling requirement. You can just open a window, that'll do that. Right. So air source heat pumps, because they're using outdoor air, expected COPs for an air source heat pump on this project was about 2.3 COP. So we were nearly doubling the COP by going to a ground source heat pump. And then we had, so if we're going to use our energy efficiently, we wanted to try to make it as efficiently as well. So we've got a big solar farm, PV solar farm and battery system. So we can collect the energy during the day and then release it through the heat pumps at night. So it's just a bit of a site overview, and you can't see it because my little picture's sitting in the way there. Let's move that over. So we had it broken down into 2 sets of bores. So we had a set 1 to 8 running along down the bottom here, supplying all the cabins. So these are all the eco cabins. You can see the solar tubes and solar voltaics. Got our solar farm over there. And then we had a set of 9 bores, which were doing the commons building, which is this building, the kitchen and the amenities block. And then a few of the small little sort of service blocks there. So we broke it into 2 halves. Each bore was drilled only 75 meters deep, so quite a shallow bore. We were down into very wet alluvial gravels. We were expecting to hit rock within about the first sort of 2 meters. We went down 75 meters and never touched rock. We were also expecting it to be relatively dry and rock. So after doing all our base calculations, we had to now do a whole complete rejig because what we hit on site was completely different to what we were expecting in that area. We had another drill job not far from there that was straight into solid rock, so we were expecting that. But you know, wet conditions, great for ground source, great conductivity onto pipe work, 100% conductivity around the pipe, so it actually sort of worked in our favor a wee bit as well. So each collector was putting out 30 watts per meter of energy that we were getting. And the bunk cabins down here were joined in a shared loop array. So a standard sort of setup for connecting up bores back to a heat pump would basically be you drill all your bores, then you have a reverse return header that comes back 2 pipes back into the plant room where you would go into either a buffer tank for the heat pumps to use. The difference with a shared loop array is, does anybody know about shared loop arrays? Is this, okay. So a shared loop array, the difference is instead of having all of the bores connect together and come back as a single pair, each building connects to a reverse return header. So it's not like a district heating where you have to have a full pump circuit going around to a centralized plant and then that centralized plant feeding back to each cabin. Each cabin works as its own decentralized piece of plant. So it means we could have small little heat pumps all connected onto a circuit and they just add their own pumping power as and when required for the cabin. It's another talk that we're going to do on shared loop arrays. It's a massive subject. And it's being a big driver in the UK at the moment to get a lot of social housing and that going is using shared loop arrays. So we'll come back to, so the design principles that we used for these cabins. So this is what we sort of broke it down to is number 1, room interface. So basically that's engaging the client in the use of the building. So we had little tablets in the buildings, and in that tablet, it was basically explaining how the eco retreat works. And if they ramp the room up to 27 degrees heat, they're going to chew a lot of energy. So we actually had energy meters for each cabin so people could see how much energy they were using. And by dropping their heat down, they could see how much energy they were saving. So it was really good for the people staying in the rooms to see the impact that they themselves have on a cabin. So that was number 1. Number 2 was passive design. So the walls and roofs were R11. So they were 300 mil thick, Kingspan SIPS panels on the outside, and then stick and insulation on the inside. So with R11 walls, R11 roof, really low annual kilowatt hour requirement. So low heating load. In slab heating is the best way to really for us in New Zealand to work with ground source heating because we're generally heating only. So we can run the slab at a much colder temperature. So only at about 35 degrees coming out of the heat pump, which again pushes up the COP of the heat pump, makes it more efficient. And then integrating the design. So actually bringing the solar collectors and the heat pump to work together, which I'll go into a little bit more in another slide. But the main thing really here is looking at it as a whole rather than lots of individual components, bring them all together as a single unit. So this is pretty much the sort of basic design of how we work the system. So we've got our collector bores down the bottom here. So this is our set of bores, and they come up and they were feeding direct into the heat pumps. Then we've got solar arrays coming through a heat exchanger. So the solar arrays were going direct to their hot water tank, but we did have a heat exchanger in line. And the purpose of that heat exchanger is when we had excess solar, so the solar had already charged the hot water tank, what we would do is we would kick this exchanger in and we'd have a little pump, and that would take that excess solar and load it down into the bores, into the ground. And the purpose of that was to charge the ground prior to wanting to pull the heat out at night. So I'll go through each sort of section one by one, ideally. Oh, a little bit of movement. There we go. So basically that one was there showing you, so excess heat has now come off of the solar panels and it's gone into the bores. So the next stage now is to basically make more heat. So it's got into the evening now, temperatures dropped quite dramatically outside, so we need to start running the underfloor heating. First thing we do now is all that loaded energy into the bores, we'll bring it up, get it into the heat pump, and that would now increase the COP quite dramatically of the heat pump. So with those bores sitting at about 12 degrees down the bottom, we could be hitting COPs of 4. If we charge down there and we can pull that in at a much higher temperature, bringing it back up to 12, those COPs can be 5, 6. So it's a big jump by just running a small little pump on a small little heat exchanger and a massive COP gain. So next, store the heat. So the heat pump now heats up the buffer tank in there. So we had 4 big buffer tanks on this job. Interesting fact about the buffer tanks, these have an anti-siphon connection on them. Standard buffer tank would just have a port straight in the side of it. These are a 45-degree drop. So that stops any destratification in the tank, but also any heat leach coming out. These tanks are actually used in Antarctica in the buildings out there because they were Belgian tanks that were ranked as probably the most insulated and well thought out buffer vessel you can get. So next, instant hot water. So, oh, jumped ahead one there, come to that in a minute. So instant hot water, so coming out of the tank, and we're using, instead of hot water cylinders, we're using instantaneous hot water heaters. So like a sort of gas Renai, but instead of using gas, we're using water stored from the tank. Purpose of that is we don't have to store the hot water over 60, 65 degrees for Legionella protection because there is no stored potable water. It's instantaneously heated. So if we only want 45 degrees out of a tap, it's a waste of energy to heat the tank to 65 to kill Legionella and then drop it down to 45 for distribution in the house. Obviously, COP of a heat pump, when you're heating to 65, 70, the COP is just nosedive. So we want to make as low a temperature as we can to keep the COPs up. The heat exchangers that we used on there were like a PAR heat exchanger in an insulated box. We had a 0.5 degree drop. So if we put 46 into the exchanger from the tank, we would get 45.5 out the other end to go to the tap. So really highly energy efficient. But again, we can run the buffer tanks at the tap temperature we want. And that was a massive saving in energy doing that way. And then the last one was pretty much efficient heating. So running in-slab heating, again, in-slab heating, we only had to run it about 40 degrees going into the slab. So all of this system, those tanks, never 50 degrees was the hottest we ever needed to get the system. Any other system, you probably have to run that up around sort of 65. So that was big saving for us. So some numbers, it's always the dreadful bit. So first of all, the loads. So got a thermal space heating load of 83,904 kilowatt hours annually. So that was over the cabins and the common building. So that was our total load. Again, with all of the work that was done to passive building of the buildings, that was probably about a fifth of what it would have been on a normal project. So we've really managed to drop our loads before we even started. So that was about 35 watts a square meter for the cabins, and commons was 45 watts a square meter. They were actually about 10 watts a square meter less than that, but we targeted just to have a bit of a safety factor in there, so we lifted it 10. Domestic hot water load was 80,000 kilowatt hours annually. So that gave us a total thermal load of 163,000 kilowatt hours. So we had 21 kilowatts over the 7 cabins. Each one had a little 3 kilowatts Kenza shoebox heat pump in it, which is pretty much about the size of a little chili bin. Very small little unit. And then we had 2 high temperature 17 kilowatt units for the commons building to do all of that work. So the actual costs of that. So looking at a cost comparison difference, I just need to try to move. Oh, this is going to be risky, isn't it? I could just count the whole thing if I'm not careful. So if we'd have gone air source heat pump, would have been COP about 2.3. Our annual running costs would have been about 17,000. Capital cost would have been about, oh, look at him, he's all over it. Would have been about 189,000. Maintenance costs, we just worked on a 2% capital cost for that figure. Replacement cost, 179,000. So that's about 95% of the original capital. Replacement value is about 15 years, mainly because the plant is sitting outside in the UV, in the cold, getting attacked, and it has large fans moving. So bearings, motors, they wear down a lot quicker. So ground source heat pump system that we actually use, COP of 4. When we were preheating the ground, we were up sort of 5 and over. Annual running costs, 10,000. Capital cost was 389,000. Basically, the capital cost jump. This is literally, by the way, just for the manufacturing, so the heat pump downstream. So this isn't everything inside. This is literally just for the plant. Maintenance cost, we're assuming it's the same as air source heat pump. Replacement cost, 233,000. We've assumed that as 60% of the original capital because the pipework that's going in the ground has got a lifespan of about 140 years now. Thames Water's just released. So we don't have to replace any of that. So that's why it's only 60% of the capital, because that's what the actual heat pump plant is. So that's the replacement period is 25 years because it's internal plant and a nice protected area. So the lifespan of the product is a lot longer. So the energy savings. So our net present saving over 50 years, 171,000. Discounted payback period on that was 18 years. Now that is quite a high discounted payback period. And the reason for that is because we have such a low load, the saving of ground source heat pump now has to project out over a much further distance. So the driving factor of the client was this one was to showcase. It wasn't necessarily driven on having energy savings. It's to showcase what you could do. Had those loads have been a lot higher, that discounted payback period would have come way down. Generally, we're looking at around a 7 to 10 year discounted payback period on most projects. So annual running cost saving, 7,000. Again, not a huge amount because our loads weren't very huge. So it's a bit of a driving factor really is what your load is. The bigger the load, the quicker the payback period and the more the saving. But the building savings themselves, so operational carbon emission saving, what have we got there? 21,000 tons kg of CO2 saved. Less visual impact by massively. There was no visual impact. Actually, they started running tours to show people the ground source heat pump and the setup down the bottom. So they actually wanted people to come and have a look at it. We also had composting toilets, which put some people off going down there because they were in the same room. But again, virtually no noise. Outside of the plant room, you couldn't hear the plant at all. So there was no nighttime noise, nothing. Which also just sort of like big to make a comment that I put on there. There was a project's just been done in London at the moment. It was a 10-story apartment and retail project in London. It was an $8 million ground source heat pump system. When the architects realized that by not having all the plant up on the top levels and all of the shafts and risers required for everything, the actual sellable space, the retail space they got back on that saving a square meterage area, they actually got a 4 million a year revenue from that space. So that paid for the ground source heat pump in 2 years. But nobody had actually thought about looking at it in that way before, of actually using, that safe space. So it's just something that's worth bearing note. And we're actually going to we're getting some more information on that job at the moment. So we'll probably do a presentation on that. So AREEA, we're here to help. So as Steve mentioned before, we're a charitable organization. Main purpose of us, if you've got, we're sort of here to help you. So if you've got questions or you don't understand, it's just, you can flick us now. We've got 9+ people on the board, but we've also, within that 9, got a massive connections outside. So we're always sort of here to help. So this section really is just to show you a little bit more about some typical myth-buster questions with ground source. So one, it's too expensive. Maybe it is, maybe it isn't. There's many ways to install a collector field. You don't have to drill. You can do horizontal collector fields. You can also do pond mats. You can use the sea, you can use rivers. Basically, once you start taking away all of the costs of drilling rigs, etc., the price of ground source drops. It's just aquafine pipe, MDP aquafine pipe, cheap as chips. So if you're next to a water source and you can just throw it in the bottom of a pond, it's now really just the cost of some aquafine pipe and your COPs have gone through the roof. So there's many ways to skin the cat. But if you don't do a proper feasibility check, really you are just sort of guessing what it is. So we're always saying, well, ask a professional. It's too risky. These are basically some of the questions that we always get put to us. It's too risky and it doesn't work. So unlike air source, ground source does have a fixed collector. Air source is just using air volume across a heat exchanger. Air volume is just an endless amount. We actually have a fixed amount. So, but as long as the design is done correctly, that's all calculated in. So we can do the bores close together. So we can use, like in our job there, dumping heat down to pull it back up. So we'll keep them tight together because we want to thermal load the ground. If you don't want to thermal load the ground, so you're not going to reuse it. You just spread it further apart. So it dissipates better. Generally, if there's a failure and it doesn't work, it's not the system, it's the designer. Ground pipe has a short lifespan, like I just mentioned before. MDPE pipe, Thames Water UK has just released the latest. It was at 80 years. They're now saying it's 140 years because they've had it long enough in the ground now to take it out and test it. And they've said, no, it's actually, if it's in If you're using it within the design parameters of the pipe, it's 140-year lifespan. So that's where we start now when we're talking about jobs, is trying to push across the collector field that's going in the ground as an asset. It's not a construction cost. Look at it as an asset. It's in there. It's going to run, if an average building life of 50 years, that's 3 building lives you're going to get out of that asset. It's fusion welded, doesn't break down. Once it's in the ground, that's it. Only if somebody physically attacks it will it get damaged, or an earthquake in New Zealand. But it's flexible when it moves, and if an earthquake was big enough to break that pipe, there's not really a building left either anyway. So next, so can't use ground source. We don't have any hot temperature or steam. Common misconception is, and in fact, we actually ourselves did it by calling this a talk on geothermal. Ground source isn't geothermal. Geothermal is taking steam or high temperature water, anything over 70 degrees out of the ground and using it. That's a geothermal system. We're a ground source simple. So we're using low temperature. So generally much shorter pipe work depths. Biggest we've sort of seen is down to 300 meters. Generally wouldn't see anything further than that. Most jobs are 100 meters. So we're just basically looking at trying to use a ground temperature that is warmer or cooler than the outdoor temperature. So obviously New Zealand, really, we're generally heating based. We're not really looking to cool. Here, you're actually completely the opposite. So you're looking to cool and not to heat. So as long as the ground is cooler than the air temperature, you're now winning. So I think what's it, Melbourne, did you say is about 18 degrees?
18,
yeah, so generally the depths we're looking at 18 degrees. So if you're using that as a feeder into a heat pump, but your heat pump, an air source heat pump was sitting there running at what, 35 degree outdoor air temperature, massive. You're so much closer to your end target already. So basically, to answer the question, it's ground source, not geothermal. Whole system fails if the pipe is damaged. Yeah, no, you just got to repair it. Luckily, especially with drilling, our stuff's way out the way. It's never going to get damaged because nobody's going down to those depths. But it's exactly the same as any other network pipe that's put in the ground. So, you know, councils, etc., they're all using MDPE pipe for their water mains because it's a good, solid, safe pipe. Will I need a backup system? Generally, a lot of people do say if you're using ground source, you need a backup for when it fails. But ground source is just as, if it's designed right, it's just as reliable as any other system. So it's like saying ground source is the backup for the gas system that could fail. Actually, I had an interesting comment about the gas that came out on the news this morning.
Yeah, it's banned from unsort of label January 1st next year. Yeah, January 1st.
So that's January 1st next year. Gas is basically banned in. Is that over the whole of Australia or just
No,
Victoria? Just Victoria.
And just on new buildings.
Yeah. Okay. It's big cool. Rule of thumb, right or wrong? Study of North. This was a guy called Ed Lorenz, which is pretty much known as the grandfather of ground source heat pumps, an American. He did a study of North American jobs, looking at feasibilities. Basically, I think it was about 800 jobs that they looked at, but 80% of viable jobs were canned or written off because mainstream consultants due to incorrect rule of thumb estimates. So this is where we're saying it really is using the right people to, and that's why AREEA is here to try and sort of help get that information. We've seen so many different rule of thumbs, but if you don't know how your collector field is going to go in, you don't know what your capital outlay is, so you don't know what your payback periods are. So it really is worth doing the assessments because these were viable projects. When they went back to look to them, 80% of those projects would have been viable. So we're saying take the guesswork out of, me, bring their accuracy in. So thermal conductivity testing. So when you're designing a collector field, most people will design using a couple of different programs. GLD is one of the main ones, American program. The program does a lot of work. You still have to input the conductivity rate of the ground, which most people is just done on a chart. But if you were looking at, say, a chart and you say, well, we've got a lot of sand in this area, depending on the humidity, the range of conductivity in watts per meter Kelvin can be anything from 0.47 to 2.2. That's a massive jump. That's going to like triple the size of the collector field based on a 10% humidity range. So a designer is going to design to the worst case scenario. So we're saying, do a test. There's a thermal conductivity test machine. You just do a little bit of pipe work, and we actually test the conductivity rate of the ground. So now all of that's gone. We have a very specific number that we can use. That test is very cheap to do. There's a few of those test machines around in the area. Generally, it's going to be £5,000 to £10,000 to do a test, whether it's a bore or whether it's just a collector field. But at least now you know exactly what your rate is. And again, it's taking out all of that guesswork, and it's now bringing some accuracy in for your feasibility. So we would always say, do a TCT test. So that can either be after the design, you've already confirmed you're definitely doing ground source, do a test on the first loop while the others are being drilled, because then we can add loops or we can take loops away. Normally we're actually taking away rather than adding, or you actually do it as a standalone test before you, as part of a feasibility. We got there, that's it. So just a couple of bits up there. Again, I'll leave the slide up here. So if you want a QR code to AREEA on there, which will take you through to AREEA's website. And if you want a bit more information about some other projects and that we've done, we've just put my little QR code tucked in the corner there. So those that are online, that are on lunchtime, etc., thank you very much for sort of coming along and joining us, and I hope you enjoy the rest of your lunch, what's left of it. And for those in the room, if you've got any questions, that yes, now's the time to stick your hand up, and I can jump back through some slides if anybody's got any questions. Yep. I hate presenting.
Just a quick question.
Yep.
Do you need a special water treatment for the borehole?
It's a closed circuit, so it's not. You can do open circuit, but we're running closed circuit. So basically, yes, it has to have antifreeze in it for us, because you can snap freeze the heat exchanger. So when you take off a massive chunk of heat and you reject a massive amount of cold, that can actually drop into negatives on a snap and split the exchanger. So we will generally in New Zealand, we'll put a 25% mix of either propylene glycol or ethylene glycol, depending on ethylene glycol pumps a lot easier than propylene, but propylene is a food grade, so there's no harm to it. It's actually worth mentioning as well, there is another type of ground source called direct exchange. So that's where obviously we're using water-based or glycol-based systems. So the only refrigerant is the very small amount of refrigerant inside the heat pump. There is another system where they take that refrigerant and they put the refrigerant in the ground. So you're now bypassing all of the pumping power and the extra heat exchanger required. We don't deal with that. We don't promote that because it is a massive amount of refrigerant. If you have a leak, you're talking big volumes of leak. And you also have to use copper pipe in the ground, which is also not going to have a 140-year lifespan. But it is out there, and it is a system that's done. Few countries won't allow it. Ireland won't allow it, basically because of risk value. But yeah, it's out there. But basically, to answer your question, yeah, propylene glycol is what we put in there, and it's a closed circuit. So,
Can you talk about how you build the borehole?
yeah, how they would drill. Yep. Yeah, so the question was, how are the boreholes go in? So if we're doing drilling, basically it's a geothermal specific drilling rig. They will drill a 140 diameter hole, and they'll basically just start drilling down. So if you're drilling into rock, we can just drill down to the depth we want. Then we get the two pipes, we fusion weld a V piece on the bottom, and then that gets inserted down the hole. And then it gets filled up with bentonite, which is a thermal conductivity grout that basically takes the air cavity away so we can conduct onto that. The only difference is if you're going into sand, you need to case it. So as they drill, they're putting in a metal casing or a plastic casing, an HDPE casing down. So when they pull the drill rig out, it doesn't just all collapse, because they have to pull the drill rig out to get the pipe in.
What about with the alluvial gravel? Did you have to case that?
Yes. Well, the other thing is if you're going into water, no. So we do have to case it to get the probe in, but then you can pull the casing out.
Right.
So because it's water basically is the key. So water is the conductor in that point. So we weren't really looking to try and get conduction to the gravels. We just wanted it in the water. So yeah, so we did use a casing to get the probe in, but then pulled all the casing out. Yeah.
Did you do much testing around the temperature
Yep.
of those boreholes before you?
Yep, we did a full TCT test on that job. So with that job with the headwaters, we actually had an existing building. So when we first started the job, we used it as a test cabin. Because a lot of the stuff we were doing has not been used before, as far as BMS control systems, it was a bit new for the client for ground source. They just wanted to make sure it was definitely going to work. Kenza heat pumps, those shoebox heat pumps. That's the first time they've been brought in. So we used that house as a test cabin and we loaded everything into it. And we actually run all these tests to help us with. So we did a TCT test on that and we got back that TCT was about 2.4 watts per meter Kelvin we were getting out of that.
What was the ground temperature, Steve?
12. Yeah.
Down 100 meters?
Yeah. Yeah, it's in water, so it was just constant. And it's slightly flowing water, which really helped us as well. So all of that rejection energy over a period of time, it was slow moving, just got taken away. Which is why when we were loading solar, we had to use it that evening because by the next day, the heat had already gone. But it was really good for load during the day, pull up at night, and we were seeing some big jumps in temperatures coming up. Yep.
And actually installing the pipe work, inevitably these contaminants get into the pipe, it's swarf or whatever in the process.
Yep.
Which with a vertical loop, then the gravity will sit in the bottom. Is there a program? Maybe at the time that builds up. Sure.
Yep.
Is there a process to
Yeah. So basically, for
for
flushing out pipe work
yeah.
was the question there. So getting swarf, etc., in the pipe. Obviously, we're going down 100 meters with a fusion welder fitting at the bottom. We don't want to have to go back down there again. It's pretty much a write-off. You have to start all over again. When you cut the pipe, you're using cutters that don't create a swarf. It's a fusion welded fitting that's then pressure tested before it gets put down. Each bore goes down individually, and then we can flush the bore before we connect the header up along the top. So basically, there's no real risk. As long as the only risk would be contractor risk of not putting a cap on and somebody drops a stone down it. But a flush would take that out. Yeah.
There's a question online.
Yep.
I don't know whether you want to call RV to pick it up or I can read it.
You might be best you read it out.
The RV is online. Ask, could you tell more about the shape of the heat exchangers you use? Did you do any efficiency studies in terms of cost and amount of heat testing for alternatives?
I'll take it this is the ground heat exchanger she's talking about. Yeah. We were confined by space on site. So the question was, did we look at other options apart from drilling, I'd imagine, for the collector field? Is that my understanding?
Did you look at whether different heat exchanger shapes, I guess, probably.
Okay, running two, yeah. So, yeah. So did we look into different types of collector field that could be used?
U-shape or W-shape?
Yeah. So basically, when you're putting your bore down there, there's lots of different ways of doing it. We can use a 4-pipe system. So instead of, we used a 2-pipe system with a V connector on the bottom, but you can get W shapes where you can actually stitch. You can get 4 that go down and connect onto a 4-piece header. Yes, there is efficiencies in that, cost efficiencies, because you're putting in less bores because you're getting more per bore out. The problem with us in the bottom of New Zealand is access to that stuff. You know, we would have had to buy that in, first time contractor would have used it. So we actually stuck with the system that's tried and tested, the driller knows and the driller can install. The driller really has to feed that pipe into the bore. If you start giving them now a 4-piece 40mm pipe, he's going to look at you and go, oh my God, how am I going to get that in? So really, we took all of that away.
What would the bore size be for a 4-pipe?
For a 4-pipe, it's probably not that much bigger. You're probably only looking at about 200 for 4-pipe helical to go down. Yeah. You are condensing a lot more, so you're not going to pull in the same temperatures because you're loading a lot more energy into a much confined space. So you do want to be doing that in a wet scenario more than anything. So if you were just in like a alluvial gravels with a bit of air pocket, you probably wouldn't do that. Probably more question if Clint was here. Yeah. Well, one of the other people on the board is a drilling contractor, so he's pretty much done every different way you can do it. Any other questions? Yeah.
Another one. You mentioned the instantaneous heating.
Yep.
And the advantage of reducing thermal losses with the storage. Can you explain that again?
Yeah. So the use of, so basically with your hot water supply, so you can either have stored hot water, storing in a cylinder, and basically you draw off of that cylinder. The issue we have is that cylinder has to hit 65 degrees once every 24 hours to kill basically any Legionella disease that could be in the tank. So with the efficiency of a heat pump trying to make up to 65 degrees, the efficiency drops right off. So by the use of using an instantaneous hot water heater is it can be a closed circuit on the other side of the heat exchanger, and it doesn't touch the potable water. So it's literally going through a heat exchanger. We've got our cold water main coming in, goes through a heat exchanger and comes out hot. This side of the heat exchanger, there's just a pump, and it's pumping the water from the buffer tank through that half of the heat exchanger and just going round and round and round. So as this comes up, that pump kicks in, heats the water as it flows through, and we just distribute it at tap temperature, which was 45 degrees for the campground. We didn't really need any hotter.
So the primary loop is connected to the heat pump.
Yes. Yeah. And a secondary loop is just the mains pressure coming through. Yeah.
That one runs at 45 degrees. So that's
Yep.
different, 50 degrees, 5 degrees.
Yeah.
different.
We were only losing like, 1 degree, pretty much 0.5 to 1 degree loss coming through. Really, and they're also, it's actually quite a modern, it's not just a heat exchanger that we just screw to the wall and put the pump in. It's actually got a lot of logic and brain built into the controller. It's a variable speed driven. It's looking at your target temperature. It's looking at the incoming water temperature, and it's got probes on the tank, so it knows the temperatures in the tank, and it's turning the pump, speeding it up, slowing it down, watching the temperature going out to keep a constant temperature. So, one of the big problems with gas instantaneous water heaters is 2 people turn the tap on, the temperature just drops. Whereas this system ruled all of that out. More flow, it sped the pump up and fed more heat in to keep it up. It was a first time we'd actually used that system, and I would use it again for sure. It was awesome. Yeah. Again, more expensive though. But it really saved us a lot on hot water energy, the amount of energy we had to supply.
So with the construction of that particular job,
Mhm.
how long does it take to bore a hole? When you've got 8 in a string,
Mhm.
does it take a day to bore a hole, the bore moves up, the
Yep.
pipe goes in? Is it like a 2-week exercise or a 4-week exercise?
Really depends on what you're drilling into. So
On
solid
that
solid
particular
rock.
job,
On that job there, it was a day of bore.
that day of bore, and then the pipe
Yep.
is the day to get the pipe.
It's the same machine actually does the drilling and the feeding the pipe in. It's all on the same rig. So basically they'll drill down, case it, put the pipe in, pull the casing out, next day, move on to the next one. There's a bit of mobilization and demobilization time that the rig is on tracks. So it's not the fastest moving thing, so it has to channel between it. But generally, we're only talking about sort of 7 to 10 meter spacing. We were actually kept it a bit tighter there because we were trying to load the thermal energy to draw at night. If we weren't trying to reuse that energy, we might have spaced them out a bit further just to stop some temperature coming. But no, that job was a day of bore. And then mobilization and demobilization time on top of that.
You're obviously using a lot of specialist equipment. How did you go with applying all that to standards and codes and limits that might apply on, hot water design, traditional?
Yep. So sort of question about best way to word that is, I suppose, with our standards, etc. I mean, the thing with ground source heat pump, and even in New Zealand, the heating industry in itself, there are no real codes or standards for it. Ground source heating, the collector side, this is why we were using IGSPA before, because that was probably one of the best standards that we had. So there isn't really a standard. You are relying on the drilling guy listening to the knowledge of the designer and doing it as per. The drilling rig itself is actually a piling rig. You can use a piling rig to do it. So it's not there are geo-specific rigs, and they're not specific because they're the only one that can do that hole. They're specific because they're way more efficient at doing that kind of work. But just a normal shaky old rig on the back of a truck will actually do the hole when you feed the pipe in. So you don't really need specifically trained contractors. You just want contractors that have got experience and got the right gear, because it's going to be quicker, which is going to be more cost effective for you. As far as standards go, that's why AREEA is here. We're trying to set up standards. There is a lot of jobs, especially back in the day. I mean, I've been involved with it for 20 odd years now with ground source in our area. There's been a lot of failures. Those failures were because the people were just doing the design on the back of a fag packet and had really no idea what they were doing. So again, like I said before, it's not the system that is the failure, it's the designer of the system that was the failure. Yep.
Maybe you want to call out Juliet online, maybe she can answer the question by unmuting herself.
Okay. How do I do that?
Hi, Steve. Do you hear me?
Oh, awesome. There we go.
Yeah.
We've got
Great. Great presentation. Thank you very much. And I don't want to keep you and the other people there in the room that are waiting for the finger foods so long. So I had a quick question.
Yep.
Like regarding, well, based on your experience, you mentioned that in New Zealand, of course, you only need heating and hot water production. Have you found or measured any long-term effect because of only heating and cooling to the soil, to the houses?
A long-term effect from heating and cooling on the bore itself?
Yeah, like maybe settlement that will cause any problem to the house or something, or not?
No, again, it comes down to the design. I mean, ground source systems have been designed since what, about the 1950s. I think they first sort of started in North America. It's been around for a long time. Technology's moved on. As long as it's designed correctly and the testing has been done, so we know what to expect. And it really comes down to spacing. If you've got a big load, say you've got, I don't know, 100 kilowatt load, and you need 30 bores, and you put all of those 30 bores in a very confined space, it'll work for about a year, then it's going to start failing because you can't collect and disperse that amount of energy in such a small space. And that's where we actually saw a lot of the failures in Queenstown, was the collector field wasn't spaced correctly. So they didn't actually calculate how much energy they can dump in the ground and how much they can pull back out again. So yes, failures, again, due to design, not due to system.
I think the question was, is the change in temperature in the ground making the ground settle or subside?
No, it's a very small amount of temperature we're actually changing really in the picture of it. We might be rejecting, I mean, Australia's going to be different because you're running it the opposite to how we run it. But in our example in New Zealand, we could start rejecting into just on the 0 degree temperature, and we'll be wanting to pull up. It stabilizes over the year. So at the end of the year, when we've been loading for the whole season, we would expect to be rejecting 0, pulling up at about 4 degrees out of the ground. Start of the season, we would have been pulling up 12, and we would have been rejecting sort of like 9 or 10. So as the season goes on, yes, you start cooling the area unless you've got water that's moving it away. But that's all just worked out in the design. We know to stay within the design parameters, and the software that's used is actually a really quite advanced software, and it can project out over 50 years. So we can draw a grid pattern in the software, and so we're going to have bores here, 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 and it will now project that over 50 years, the effect on the ground that's going to happen based on the conductivity rate of the ground, the diffusivity rate of the ground, how it actually spreads the heat out. So it's all programmable, it's all calculable. You've just got to know how to use the software. Any other questions? Finger food? Hey, well, thank you very much for coming along. Oh, sorry.
Sorry, just one more.
Yep.
I don't know if you had one of the earlier slides, if you compared the open system to this closed system.
Yep. Open systems, we've got the Hilton Hotel in Queenstown and our Lakes District Hospital. They run on an open system straight from the lake. Really clean water, Lake Wakatipu. It is a really good way of doing it, but you do need a lot more pumping power to do it. You need to move a massive volume of water through an exchanger and back down. So you need like a whole maintenance team, basically cleaning filters, checking pumps. Yes, it can do it. There's probably only certain places you can get away with doing it. Camp Glenorchy, we couldn't have done that. The alluvial gravels would just have too much stuff. We'd be blocking the filters every other day.
So I worked in Christchurch for 3 years.
Oh, yeah.
They went through a stage where everything was ground source and it was all
Taking it from the aquifers.
Yeah.
Yeah. Bit of an issue going on there. So these are like open well systems, so open source systems. So if you've got aquifers of water, which is basically water channels running through the block, bit of a problem that we've seen been coming up recently is if you extract the water out of a top layer aquifer and you redirect back into that top layer aquifer, you're now actually warming the aquifer. Anyone who's doing the same downstream is now getting all your rejected heat. So the standard was to take from one aquifer, but reject into a second aquifer, a lower aquifer. What we're seeing now, though, is they're actually starting to dry the aquifers out because there's so many people doing it that aquifers are actually running lower in water. So personally, we will only do closed loop because closed loop we know has a full lifespan. There's nothing that's going to affect it. Once it's in, and it's always going to work to the same design. As soon as you start taking water, any changes to that water, you're going to have changes to the lifespan of the system. They also had a bit of an issue when one of the rejection pipes hadn't been connected properly on its fusion well fitting, and it started blowing gravels out, which then created sumping. So again, not a system issue, but an installation issue that caused a problem. So what I'll probably do is just close off there, just so you know, everybody that's sort of on their lunch break can shoot off. But if I'm hanging around here for some time, so if you want to just come up and chat individually afterwards, yeah, feel free to come and chat with either me or Steve or Guillermo, or we've got Peter here as well, who's hiding somewhere, hiding in the corner. All right, so yeah, thank you very much for coming along. Really appreciate you giving us your time.
Thanks everybody for coming, much appreciated. We're looking to do a seminar similar to this perhaps once every 3 months, so keep an eye on the website. It will tell you when the next one is and where.
We're following the next rugby game, so we see.
Yeah. Cricket, by the way.
Lucky timing that. Listen, thank you all. Yeah, so there's some bigger food next door with you.